I can get that done now. All right, if I were on the right page, that would help. All right, Fred's here. JB's not here yet. Frank is here with Fran. Okay. Devin is here. Dawson's here. Cedric is not here yet. Okay. Bree's not here yet, or we haven't seen her at all. Josh not here. Taylor not here. Elace not here. Ayana is not here. We haven't seen Taiwan. Jake's not here. Bill's here. And Chuck and Griffin are here. Bottom part of that. I'm getting strong. Okay, 1, 2, 3, 4, 6, 7, 3, 4, 5, 6, 7. Got it. Okay. Now, got to back up until I can find room to work. Oops. Okay. Can't think of any major announcements. Those I've already said. For instance, there is a faculty meeting tomorrow afternoon, but they said we're not supposed to cancel classes. So I'm not planning to. But if you are in a tomorrow afternoon class, Thursday afternoon class, you might just check with the instructor just in case that instructor has to be at the faculty meeting. But the odds are they won't be canceling the class. Number 2 is I've got a doctor's appointment, eye doctor, across the street here at 8:15 Friday morning, so I won't be on the Birmingham West campus until somewhere around 10ish or so, I think. I don't know how long the appointment will take. I don't know anything else about it, so I'm guessing around 10. I may be there earlier. It may be a little later. Okay. And those are the only ones I know of. But let me also, as I've harped on before, this class, I still one research paper in, okay? Need those in, folks, but y'all have been really good about getting your first test in. There's just 2 people who have not turned that in. And then second test, I've gotten several of those as well. So if they come out, they may have already come out, I just haven't seen it, with midterm progress reports. There's people who haven't turned in anything, they're not going to have a good report, but it doesn't really matter much. But just to let you know, that is coming. It's preaching to the choir here because y'all is all in pretty good shape. Okay. I think we're on example 4 on page 212. Any questions on anything we've covered so far? No questions? All right, here's example 4. Sketching the graph of a radical function. It says analyze and sketch the graph of this one. F of x is equal to 2x to the 5/3 power minus 5x to the 4/3 power. Okay. Now, where would you begin? It says sketch the graph. What would be some things that would help you find or sketch that graph? Now, this is a little, not really tougher to do, but in some senses a little bit different. We're just not used to radical functions, probably, especially sketching them. One of the first things we usually do is talk about domain, though I don't usually talk about it in terms of domain. It's just any place where this function is not defined. That's the big question. Are there any x values for which that function is not defined? And that would be your domain, basically. Any? No, because x basically we're talking about cube roots here, and the cube roots of things of higher powers, and yeah, you can put in any number, positive or negative. Square roots, no, you can't put in a negative number, okay, but cube roots you can. None of these are in the denominator, so 0 is not an issue, so no, domains are real numbers, okay. So that's covered. The range, I think, will also be all real numbers because you have a negative in here. Raising it to the fifth power keeps it negative, and cube root of a negative number is negative, so you can have negatives and you can have positives. Same thing, deal with that. If cube root of positive numbers are positive, so no problem there. Okay. Now, I can't think of anything else to say just about the function, so where would we go next? Just sort of get an idea. No vertical asymptotes, and not likely to have a horizontal asymptote either, but we'll see. So what would you do next? Take a derivative, why not? L prime of x. And what would that be? Anybody? What would be its derivative? Anybody?
10/3.
Second? 10/3, yeah, okay. 10/3 x to the
2/3.
second?
2/3.
2/3, right. All right, here's the lace.
Good morning.
Good morning. Okay. It's the first part of the first derivative minus, a little louder, and here, set it. Okay, got it. All right. All right. Any, okay. No one else came in since I called roll. What you got for the second part of the first derivative? A little louder. 20/3 minus 20/3 x to the 1/3. Okay, subtract 3/3 from 4/3, you get 1/3. Okay. Now, what are we interested in that first derivative? I know it's just fun to take them, but why? What would be the point? What are we interested in? Say again? Critical values, and what would they be? Or either, the first derivative is 0, so we'll first set it equal to 0, okay? And what's the other one, just for instance? What's the other possible critical values? Where it's not defined, right? Okay, it doesn't exist. Very good. Does this not exist anywhere? Okay, rather negative question. No, this exists everywhere. Again, same logic as before. Positive numbers are fine, negative numbers are fine. Nothing's in the denominator, so there's not a 0 issue. So yeah, this is perfectly fine everywhere. So we don't have to worry about where they don't exist. But what we do have to worry about is where they might be 0. So, can anyone come up with at least one value for which, well, what would you do to proceed with that equation right there?
Raise everything to the 3rd power.
A little
Raise everything to the 3rd power.
All right, I was afraid we might say that, but I don't think that'll quite work because then you'll have some mixed terms in it. So now, sort of would if you move one to the other side, okay? But I would say first, what do you say? Yes, let's factor first. What can we factor out? Anything? What's that? Okay, how about factoring out 10/3?
Oh, that's a 10.
Yeah, it's okay. Making fun of my writing. That's all right. I'm not at all hurt by it. Okay. 10/3. What else could we factor out? X to the 1/3. Yeah, let's factor all that out. And then what do we have? Say again? Really? Let's see, is that right? Yeah, you're right. Wait, yeah, x to the 1/3. Okay. Because when you multiply two bases, you add the exponents. That's right. Okay, minus. Not 2/3. You already got out the third. 2 minus 2, right? And that's equal to 0. All right. Now, what's the first factor give you? Okay, what you can do is say each of these equal to 0, right? 10/3 times x to the 1/3 is equal to 0. Now we can cube both sides if you want to. Or, what's this one? X to the 1/3 minus 2 equals to 0. Okay? What value of x will make this true? X equals 0. That's it, folks. It's x equals 0. We don't need to multiply both sides, that's just x equals 0. How about the other one, though? Goodness gracious, where did that come from? What's that? Okay, yeah, x equals 8. We'll make that 0 because the cube root of 8 is 2. 2 minus 2 is 0. All right. We have two critical values. Okay? Now, what? All right, we'll keep those in our mind and let's proceed. What would we do next? We could do a little bit with those, but I think if we continue our process, we can eliminate a few, we can do some things a little more efficiently. Take a second derivative, okay? Now, I'm running out of room at the bottom, so I'm going to do it here. F double prime of x is then going to be what? A little louder. Okay, did I hear a 29ths? Is that what I heard? Yeah, that's what I thought it was. Okay, 29ths x to the negative 1/3 power. You subtract 3/3 from 2/3, you get negative 1/3 minus what? 29ths again x to the negative 2/3 power. Okay? Okay. We're not quite going to set it equal to 0, but we will in a minute. Why even mess with second derivative? What does it tell us? Second?
Concavity.
Okay, it will tell us concavity, and what particular points would we be interested there? Inflection points, okay? Now, what would be true of an inflection point regarding a second derivative? Either equal to 0 or does not exist. Okay. I think this one is easy to see a do not exist in here. What would that be? Where would the second derivative not exist?
Where x is 0.
At x equals 0, which is interesting because that was one of our critical values, where the first derivative is 0, but the second derivative doesn't even exist there. Interesting. Okay, so x equals 0 is a contender for our attention. Well, I'll put it that way. Now, is there another one here? Ooh. That's the only one where it doesn't exist. Let's see what we can figure out about where you could, it might be 0. So now we're going to set this equal to 0. Started to do it before, but that was jumping a little too far ahead. What would you do to determine that? Anybody? Factor out a 29th x2. Now here's the issue. What are we going to factor out here?
Minus 1/3.
To the minus 1/3. Let's do that one and see what happens. Okay? And what do you have left? 1 minus
X squared.
x squared. Okay? That's a 1/3 there. Looks like a 2, but that's a 3. Okay. All right. Sorry about that. All right. Looks more like a 3. All right. Let's see. Did that work out right? Okay. Let's see what happens if we multiply back 3. The 29th we get, minus we get, and this would be x's that multiply the same bases, different exponents, add the exponent. Sure enough, that gives you. Or it does, yeah.
No.
Huh?
That's not right, is it?
No, it isn't. That's what I was thinking. Okay.
That's 1/3. No. That's 1/3.
Yes. Well, no. How about just x? Oh wait, no. X. Yeah, x is a negative 1/3. Okay. Yeah, because then you keep the base, add the exponents, that works for you, right? So therefore, I was thinking maybe it's a better idea to factor out the negative 2/3. That just shifts our problem around a little bit. But this will still work, okay? And obviously here, we still have the problem with x can't be 0, because, or the second derivative is undefined at x equals 0. But what we have here is 1 minus, I'm going to write this as the cube root, let's see, 1 over the cube root of x is equal to 0. So what could we do here? Or can you see something right now that might work? That's a cube root, I'm sorry, okay. Cube root of x. Say again? Say again? Okay. Okay, say that one more time.
Add 1 over x cubed to both sides.
Okay, we can do that. Plus 1 over cube root of x. Is that what you're saying? Okay. To both sides. Okay. And that will give us 1 is equal to 1 over the cube root of x. I just got it backwards. Cube root of x. Okay. Can anyone think of an x that would make that true?
1.
1. Okay, we could have done it up there too. Okay, yeah. X equal 1 is our other critical value. Okay. Not critical value. Point of interest for your second derivative. Okay. Now, so the other thing that we want from our second derivative, since we've got it, is there. Now forget about the equals 0 for now. We know the second derivative is undefined at 0, but it'd be a good idea to see what it is at x equals 8, wouldn't it? Because that tells us whether we have a minimum or maximum, depending on, as Dawson said, the concavity. So let's plug in x equals 8 there. And what do we get? 29th over 2. okay, minus, okay, let's write that down. Okay, when you plug it in 8, you get 20/9 over 2 times 1 over 2 minus 20/9, and that would be times 1 over 4. Right, good. Okay, well here, that would be 10/9 minus 5/9. Now, we're really not too interested in what the value of that is. I'm more interested in what the sign of that is. What is the sign of that? Say again? 10/9 minus 5/9. Say again? Okay. Yes, it's positive. That would be 5/9. Okay. Pretty easy to figure. Okay. So, with that being positive, what does that make this? X equals 8. It's what? It's a concave up. Perfect. Okay. Now, we still have that issue with the first derivative being 0 and second derivative undefined. Okay? Now, perhaps it will help to plot a little bit here, and I don't have much room at all for a graph. What I think I'll do is pick another color. You pick a color.
Green.
Say again?
Green.
Green? Okay, I'm going to go with the dark green, if that's okay. So that way, I'm not going to pay any attention to my writing behind it. Okay, what is the value at some of these points when x equals 0? What would be the value there? Oh, good. Here it is. I'll find you in here somewhere. Iana? Iana?
Yeah.
Iana, okay. Okay. I've been practicing it, but when it comes to time, I try. Okay. So, what's the value when x is equal to 0? What is the value of the function? 0. Okay, that's good. Right there at the origin. Okay, we got a point. Let me tick off a few points. There's 1, 2, 3, 4, 5, 6, 7. I need to go at least 8. Okay, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. Okay. Now, the other point of interest, oh, there is one at 1, okay? What is the value when x equals 1 of your function? Anybody? Say again? -3. Okay. I'll buy that one. So x equals, okay, here we have a -3 here. Now, remember, that's not a critical point, but it's a place where we have potentially a change of concavity, okay? Because the second derivative is 0 there. And then the other point would be way out there, x equals 8, and what do we know about that? Oh, let's just plug it in. When x equals 8, what do we have here? Woo! Say again? 5 over 9? The function, yeah. Okay. The cube root of 8 is 2, and 2 to the 5th power is 32, times 2 is 64. Let's keep that in mind. Minus, and the cube root of 8 is 2, to the 4th power is 16. 5 times 16, is that 80? No. Yeah, okay. So that would be minus 80. Okay. So this will be a minus 16, right? Whoa! Way off scale down there. So it's going south fast, okay? And that's where your second critical point, and that's where the first derivative is 0, and it's concave up.
14 minus 80 is...
What's that?
14 minus 80 is 66.
That's a 64.
No, that's a 6, 64. Making fun of my writing. I'm used to it by now. Okay. All right. Got it. Okay. Sorry about that. Ugly. All right. So, but we do know it's concave up, so it's going to be rising after that. Okay? Okay. So here's what we've got. I can't draw the graph of it, but we do have these points there. The other one we didn't do intercepts, did we? We did a y-intercept without worrying about it, and it's an x-intercept too at 0, 0. But we didn't set the function equal to 0. We did the first and second derivative. We didn't set the function. What happens when we set that equal to 0? I'm going to go back to my dark color. Okay. Ooh, what would you do here? Can't factor out a numerical value, but you can factor out which one? X to the which? 4/3. Let's factor, out an x to the 4/3. And what do you have left? X to the 1/3 minus 5. Okay? And that's equal to 0. Now we already know x equals 0 is going to be an intercept. We got that. It's the x and the y intercept. Okay? But what does this tell us here? 2 on the cube root of x minus 5 is equal to 0. What could we do with that? Anybody? Add 5 to both sides sounds like a capital idea. So that would give me 2 times the cube root of x is equal to 5. And then, we could cube both sides if we wanted to. Divide by 2 is what I would be tempted to do first, but it may be actually better to do it the other way. Then cube both sides, and you get x equal 125 over 8. Is that right? Yeah. And someone with a calculator figure out what that is. That's about 15 point something another. Well, they just leave it 125 over 8. Somewhere way out there you have another, around 15 or so, you're going to be out here, you have this coming back up. So sure enough, we knew it was going to have a minimum down here, so it has to come back up somewhere. Now, what in the world is happening here? First derivative is 0, but the second derivative is undefined. Okay. Which means, and I think probably what you'd have to do is do a test point and do it for just about anything. Do a -1 here and figure out what the f value is, the function value. Pretty clear it's going to be, well, maybe it's not clear though. Let's.
It'd still be a -3.
What's that? What you could do is plug it in. Well, just plug it in anywhere, there or here. -1 will work really well in any of these places. What would you have it here? Cube root of -1. -1 to the 5th power of b. -1. 2 times -1 is -2. -1, cube root of that is still -1. But -1 to the 4th power is +1. But then 5 times a +1, -5 times +1 would be -5. You wind up with -7. You're way down south here. So we know the function did have, it has to be coming down here, it has to be coming down there. So what we have is a function that has a first derivative there, that's 0, but there's a problem, Houston. And what is that problem? I don't think the first derivative will tell us very much here. It would have, it told us increasing here and decreasing there, but we know that. Let's do the, well, we already tried to do the second. Let's do the second derivative here, and we know it's changing here, because the second derivative is 0. Let's do the second derivative here at -1. Right here, okay? Cube root of -1 is -1, so that's in the denominator. So this will be a -29. And cube root of -1 here, -1. So you square that because of the numerator there, and that becomes a +1. So that's -29. So you got -49, okay? Which is negative. That's really all we're interested in. So it's concave down here, which it almost has to be to have a 0 here. But what is it over here? Let's do, I hate to do this. Let's do a 1/8. I was going to say a 1/2, but I think I prefer a 1/8, don't you? And what's the cube root of 1/8? Oh, come on.
1/2.
1/2. Okay, but it's in the denominator, so that's 2, right? Okay, so this will be 49ths here, right? And over here, cube root of 1/8 would be 1/2 in the denominator. Okay, so that would be a 2, and square that and you get 4, so you get -49ths, -89ths here, and a positive whatever that was here, 49ths here. So that winds up being negative. So it's concave down here. Well, why in the world do we have a second derivative undefined? Well, it didn't change its sign, did it? So it was the first derivative, it was going down here and going down here, but here we do have a change because the second derivative is positive. It heads way down here, intersects that, and then heads on back up from there. So that's kind of how it looks, okay? It's a messy thing because it's a huge scale on this, and I didn't plan ahead for that. But here's what we have. If you look in the book, you'll see first derivative is 0, has to be because, you know, but you don't have a change of an inflection point there. The second derivative is negative on both sides, but not defined at x equals 0. Okay. Now, all right. Your table there probably helps a little bit. We didn't plug in all those values, but that's what you got. But we got a really good idea of what that function looks like, given that I didn't have the scale to do the drawing. All right. Not, okay. Plan ahead. I didn't. So make whatever adjustments you need. Let's do example 5 now. I should have asked any questions there, but I wanted to get that off the screen as soon as possible. Okay. So let's do example 5. Now this one, you can see larsoncalculus.com for an interactive version of this type of an example. And here we have f of x is equal to x to the 4th. Oh, I'm missing my radical expressions already. Oh, minus 12x cubed plus 48x squared minus 64x. How much longer does it go? Okay, no, that's it. Now, there's your function. Now, they say begin by factoring, which is not a bad idea, but it's not going to help you in taking your derivatives. So come back to this for your derivatives. But why would they want you to factor? Okay, let's start over. What's the domain of this function? All real numbers. This is a good old polynomial function, right? What's the range? Probably not, because this is a maximum. Next one here is 2. That means it's on the up and up. Very large x is going to be very positive, very large negative x is very positive, very large positive. So it's going to have some minimum down here that it's got to turn up from. You can't get huge negative numbers here. You can get big ones, but not going to infinity, because your end behavior here is up and up. So there is got to be a minimum somewhere in there. So we don't know what it is, but we'll wait on that. So perhaps that will be helped a little bit if we do factor. We'll see. Okay. So the other thing that would be helpful to know are our intercepts. Okay, and that's where factoring comes into play. Well, okay. Can anyone tell me the y-intercept right off the top? 0. Okay. So we know a point on this graph is 0, 0. Okay. Now let's factor. And what does that leave us with? X cubed, 12x squared, 48x minus 64. Now, what would be probably a good thing to try next, and this is mostly because this is it's not going to work, but worth an effort. 4-term polynomial, about the only way to factor that by the old school method is factor by grouping. Not grouping, whatever. That's not going to work though, because this will be x minus 12 basically, and this will not have an x minus 12 in it. No way. So worth an effort to look at that, but it's not going to work. Okay. I don't know how much time to spend on doing this. I guess they do it. So does anyone remember the next technique that we had to determine that? If you can't factor, remember the good old rational zeros test? Oh yeah. Good stuff, wasn't it? The rational zeros test says take the constant term, get all the possible factors for that, and divide it by the coefficient of the leading term, all the possible factors of that. The good news here, that's 1. So basically all the possible factors of 64. Can anyone name what those are? Plus or minus 1, plus or minus 2, go on. How about 4, 8, 16, 32, and 64. Okay. Now, we want to know if any of those are 0. Will give you a 0. Okay? I can do the positive one pretty easily, because you put a 1 in here, it's just your coefficients. This add up to be a minus 76, and that adds up to be a positive 48. So plus 1 is out of there. Okay. Wait, there is something else we can do. Remember good old Descartes' rule of signs? Oh, sure we do. Okay, what does that say? Let's count the number of sign changes we have in your polynomial here. Go from plus to minus, 1, 2, 3 sign changes. That means you can have either 3 or 1, subtract 2 from that, positive real zeros. Okay? So we know that you have 3 or 1 positive real zero. Now, if that's the case, you can almost bank what the second half of Descartes' rule of sign is, plug in a negative x here. That would be a negative x cubed But when you square a negative x, you still get a positive, so that would be negative 12x squared. Plug in a negative x, that's a minus 48x. And plug in a, you don't get anything, that's a minus 64. How many sign changes you got there? None. So you have no real negative zeros. So we won't look anywhere to the left, okay? That eliminates a lot for us, doesn't it? Okay, so this tells us no negative real zeros. So since we have, while I've got my eraser here, let's just take out all those negatives. Well, let's just take out the signs. They're all positive anyway, right? Be easier for me to take them out than try to only do the negative. That is a 64 at the end. For those who want to make fun of my writing, it's a 64. Okay. Now, after that, basically, our technique is synthetic division. We take each of those and divide it into this. If we get a 0, that's a 0 for the function. So we know 1 won't work, so let's do 2. And then what is synthetic division? What do you write down? Coefficients. 1 minus 12, 48, minus 64. Oh, don't you love pre-calculus algebra? Okay. Skip a line, draw a line. Remember how this goes? Bring down the 1, multiply, 2, add, negative 10, multiply, minus 20, add, 28, multiply, 56. Not going to work. So we'll forget 2. That doesn't work. Remember this or not? Too long ago, right? Okay. Let's try 4 next. Okay? Okay, with 4 we get 1 times 4 is 4. Add, you get a minus 8, negative 32, 16, 64. Ding, ding, ding. We have a winner, okay? It's a 0. That means x equal 4 is a 0 for this function. All right. Want to try 8? Okay. I know you do. So we'll try. So, let's do this. Whoops. Okay. So x equal 4 is a 0, so that means 4, 0 is another x-intercept. Okay, so 4, 0 is another x-intercept. So now let's try our 8. Okay. Oops. Okay. Not looking forward to this at all. Okay. 8 times 1, 8. That would be a negative 4. Oh, boo hiss. Minus 32. That'll be a 16. And that will be way too big. Right. We know it won't work. Okay. Why is this not working right? That should have told us, don't look any further. There aren't any zeros beyond that. That's the upper bounds test. But it didn't tell us that. So then we'd have to try 16. I think 16 will work. So we'll try 16 in there. And that will be a 16. Yeah, this will work. 4, 64, huge number, not going to be a 0. And all these would be positive numbers. You know, you don't even try 32 and 64. They're just going to get worse and worse and worse. Now, I'm sort of upset that 8 didn't give it to us, because I would have guessing that 8 might be a 0, but it's not. Okay, we know that. It's not. Nothing beyond that. Those are your rational zeros. 0 and 4. That's all you got. Okay? So, those are done. X-intercept 0, 0, 4, 0. Y-intercept 0, 0. Okay. So I don't think we need the factored form anymore, but just in case we do, I'll leave it there. It's not taking that much room. All right. Now, if you have better ways to do this, by all means use them, but that's finding your zeros. Graphing calculators will work pretty well too. Okay. So, I think we got everything out of the function we can. We will come back and use it if we need to. Except, what's another thing we can do? Take a derivative, f prime of x is equal to what? I'd go back to the top one rather than using a product rule. What do you get? 4x cubed got it? Ah, come on. Those calculators slow you down, don't they? Got it. Okay, is that what you got? Now, what would be the first thing I hope that comes to your mind what to do with that? Yeah, let's factor out whatever we can here. I know 4 will go into 69 and 64. Will it go into 96? I'm pretty sure it will, won't it? Okay, so let's factor out a 4. That leaves us an x cubed minus 9x squared. 4 will go into 96. 20 what? 24 times, okay. Plus 24x minus 16. Is that right? All right. And again, you might think of doing factoring by grouping, but it's not going to work here either, so we won't worry with that. Okay, now we want the places where that's equal to 0 are not defined. I'll do the not defined part, okay? As the polynomial is defined everywhere, okay? I got that taken care of. You don't have to worry about it. Okay, now where is that one 0? Well, we've got to do almost the same thing we did before. And the Descartes rule of sign is going to give us the same thing before. You're going to get 3 or 1 positive real zeros. You'll get 0 negative real zeros. So let's just go with the positives. And the possible factors for 16 are 1, 2, continue, 4, 8, and 16, right? We don't need the negatives because the Descartes rule of sign will give us the same result we did before, minus, 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 okay. So, 1 is easy. All you have to do is add the coefficients. These two add to. Pull out the calculators, okay. What do these two add to? 25. These two add to? 25. So x equal 1 will be where your first derivative is equal to 0. So f prime of 1 is equal to 0. So there's a critical value. Okay. Now, to see if the others will work, synthetic division is helpful. Let's go on and use the 1. We know it works, but it will make the whole process simpler. Coefficients are 1, negative 9, 24, and 16, minus 16. By the way, if you are ever missing a term, you have to put in a 0 there when you do synthetic division. Remember? Okay. So skip a line, draw a line, bring down the 1. What do you get here? Multiply. 1, subtract, or add. Negative 8, multiply. Negative 8, add. 16, multiply. 16, and you get your 0. We knew that was going to happen. But here is the good news, folks. What does this represent? That was a cubic polynomial up there. This is now a quadratic. X squared minus 8x plus 16. Can we factor that? Yay or nay? Okay, how does that factor?
Minus 4 squared.
X what? X minus 4. Perfect. So we have a double root here at x equal 4. Okay? And that's another place where your first derivative is equal to 0. So x equal 4, though, is this one too. So this is also f prime of 4 is also 0. So not only is it a 0 of the function, it's also a critical value, x equal 4. X equal 1 is a critical value here, but it wasn't a 0 of the function. Okay. Now, sort of feels like time for second derivative, doesn't it? I'm rapidly running out of room here, so let me erase some of this stuff that is just scratch work. We'll erase these and those. Okay. All right. What's your... I guess we need to keep the whole thing. What's f double prime? With the 4 in there. 12x squared minus 72x plus 96. Okay. Now, we're interested in where that is either not defined or equal to 0. And certainly we can factor out a 12 out of everything there. And what do we have left? X squared minus x plus isn't that 8? Those calculators slow you down a little bit. Is that right? Okay. Does that factor?
Yes.
Yes, how?
X minus 4 and x minus 2.
X minus 4, x minus 2. So we have, good old boy, that 4 is overworked here. The second derivative of 4 is also equal to 0. Okay? But now we also have one more. The second derivative of 2 is equal to 0. All right. Okay. So I guess we're ready to do our green graph again. Is that right? I'm going to sort of arbitrarily do this. I may not be right on it, but it'll be close. Okay. Okay. Now, we know that the function has a 0 at 0, 0. And we know it has a 0 at 4, 0. I believe that's right there. Okay. We know the function has a first derivative equals 0, x equal 1. So it'd probably be a pretty good idea to figure out what f of 1 is. Let me keep, okay, f of 1. Now we already did that once, so I didn't write it down, did I? Okay. And that's pretty easy by just adding our coefficients, right? And we did that already. That the negatives had to be minus 76 and a plus 49. I do want to calculate on that one. Minus 76 plus 49. Is that 17? Uh-huh. -17. All right. The old gray cells, they get
Minus 27.
27? Okay. Minus 27. So, wow. I sure didn't need a different scaling here. So, f of 1 is negative 27. It does go way down there, folks, but I guarantee you it's going to come up from somewhere down there. So, there is a critical point, and we can go on and plug in. We know that the first derivative, yeah, that was already known to be 0 there. Let's see what our second derivative is there. So you plug in a 1 here, or plug it in here, that's easy, okay? Add those two to the positives together, you get 108 minus 72 is 30, well, it doesn't matter, it's positive. It's way positive. So we know it's concave up down there. Now, I'm going to hazard a guess here and say that's going to be our minimum because it's concave up, on one of two places where the first derivative, okay, and this, now we've got, I've got to find the right class here. Taylor, right? All right, good deal. Okay. We're in the middle of example 5 on page 213. It is sort of long. Not hard, but long. Most important thing is bookkeeping, okay? So we know f of 1, that's where you have a first derivative. We know the value there is at minus 27. It's first derivative is 0, second derivative is positive. Wasn't it? Yeah. So it's concave up big time. So that, I think, is going to be the minimum for the function, okay? The only other place where the first derivative was 0 was at x equal 4. We already know that. That's this point right here. So 1, you're way down here. At 4, you're up here, okay? But also, the second derivative is 0 there, which means you have a change of concavity there. Now, the only way your first derivative can be 0 and you have a change of concavity, first derivative is 0, meaning it's smooth. Remember the last one, first derivative, the second derivative not 0. This one, the second derivative is 0, so it is changing sign there. So that is an inflection point, okay? Almost definitely, okay? Oh, let's see. No, it wouldn't have to be definitely, but I think it's a pretty good bet that's going to happen there. And here's part of the rationale. Remember we said at the very beginning, this function is on the up and up. It's negative here, 0 there, and it has to be positive here. It has to. It can't come back down again. It can't come back up again, or else we'd have another 0 in there. Oh, wait. Or did we? No, we don't have another 0, do we? Those are the only two zeros we have. So I think we can be pretty well convinced of that. So I think what this function is going to look like, it has to be coming down, and we could even plug in f of minus 1 if we wanted to, but it's going to be coming down here, and it crosses at 0. It doesn't bend or do anything else. It crosses because that's that 0 is a single 0, you know, the multiplicity of 1, okay? And then it comes down and hits your minimum somewhere way down there, comes up here, and then does this kind of a number here and goes on up, okay? So I think that's what the function looks like, and if you look in the book, that is pretty much what it is, okay? Oh, and we never did mention this. The second derivative, remember it's concave up here, somewhere here it goes to being concave down, and then concave up again, because you have another point of inflection at x equal 2. No, I'm sorry. No, I mean the x equal 2 was that point of inflection down. It's 1 is where your minimum was, and then your point of inflection. Concave up here, concave down there. I put it in the wrong place. Okay. And that's an exaggeration because it needs to be way further south than that. And that's one thing we didn't do. We didn't plug in what the value at 2. Forgot about that. We should have figured the function value at 2. But I wanted to leave that to the student because that's too hard for me to do in my head. Okay. So you got calculators. Punch it in and see what it is at 2. Somewhere way down there, it changes from being concave up to concave down. And then it changes again from concave down to concave up at 4. Okay. All right. Take your time on these. Okay. You see there's lots of places where things can slip up, but take your time, record everything, be a lot neater about it in a table. You got more paper than I have drawing space here, so knock it out. All right, any questions on that? Let's go on to example 6. Okay, do I really want to do this? Oops, my eraser is not erasing. Okay, let's go back to pen color there. Okay, there's one. Yeah, we got plenty of time. Let's do example 6. Analyze and sketch the graph. Oh, yeah. Okay. F of x. In fact, just to give myself a little more room, let's just start this thing up here. Okay. F of x is equal to cosine x divided by 1 plus sine x. Okay. Now, where is usually a good place that we start these things? Okay, the domain. And what would be of concern to us in the domain here? The denominator can't be. And where is that denominator 0? Okay, let's write it down. Denominator, which is 1 plus sine x, cannot equal 0. We know that, right? Never divide by 0. So what? Yeah, let's say it again. Okay, let's do it. The sine x, then, cannot equal -1 if you subtract 1 from both sides, right? And then you're answering the question, where is sine x -1? 3 halves pi, and every 2 pi added to that, right? So, let's go on back to green, since we've gotten into that mode here, and have our graph here. Okay. So, let's just tick off a few things. 1, 2, 3, 4, 5. This is not going to be the scale, so don't start screaming and yelling. I'm going to do these in half pies. So this will be pi halves, pi, 3 halves pi, 2 pi, 5 halves pi, 3 pi, 7 halves pi. Okay. We know you can't, and this is negative pi halves, negative pi, negative 3 halves pi, negative 2 pi, negative 5 halves pi, and negative 3 pi. You can write more, but I don't have room. Okay. Now, we know that your sine is -1 at 3 halves pi. So I'm going to change color again because I like to put vertical asymptotes in red, meaning don't touch it. Don't get close, okay? And every pi from, or 2 pi from there, I'm sorry, I said pi before, every 2 pi from there. So that would be here and here, right? And here. Okay, those are pretty ugly vertical asymptotes, aren't they? Okay. Those are your vertical asymptotes. Every 2 pi from 3 halves pi. Yeah. Hope I've got it right. Okay. Good place to start. Okay. Let's go back to, I don't know what color I want now. Let's go back to this one. Okay. So we got our domain represented by vertical asymptotes. That's where the function cannot be. Okay. Anything else you can tell me about this function? We got the domain part, vertical asymptotes, where the function cannot touch or cross. What else can you tell me just from the function? Not going into any derivatives yet. What's usually next? Second? Oh boy. I don't want to mess with that quite yet. I don't think there is one, but we don't really have a good rule for that. So let's not do that yet. You're probably right. No, I don't think you are. Okay. Anyway, how about Nick Saban's big on defense, right? A few years ago, they had so many intercepts. Oh, intercepts. That's right. That's what we're dealing with. Okay. What about our intercepts? 2 types. What are they? X and Y. Okay, which one to go for first? One is really easy. Why? I thought you'd say that, you lazy thing. Okay. Why? Because that's where x equals 0. When cosines equal 0, what's your, what is cosine of 0? 1, and sine of 0 is 0, so you got 1 over 1. So our y-intercept is at 1. And this is the part I said is not to scale, because I'm not going to figure out, these are going to be numbers here, not fractions of pi, okay? So, well, let's see. I don't want that. Okay. So, y is equal to 1. That's our one and only one y-intercept. Okay. Now, what's the other kind of intercepts? X-intercepts. And where is that true? Where y is equal to 0. Now, in that function, what's your y? F of x. And how can that f of x ever be 0? How can a fraction ever be 0? Anybody? Yeah, you never set the denominator 0. Numerator. Anytime the numerator is 0, the whole fraction is 0, right? Okay, so where is cosine 0? At what values? Okay, all the half pi's. So I can do this one, but I'm not going to do that next one, because we can't go there, because that's where the signs equal -1. So I'll skip that one, but I'll do this one. Can't do the next one because sign would be 0. You know, that makes your denominator 0. And then I'll do this one, and I'll do this one over here that I didn't label, but it's also there. All right. Now, this is a periodic function. So sadly, we don't have to do anything else, okay, to sketch the graph, because you know it's got to be coming up this way. And unless it turned and went up, which it doesn't do, it's going to be heading down that way. And if it does that here, it does it here, it does it here, it does it here. Okay? Now, I'm convinced that's what it's going to look like, just from those 2 points we had, and then those other x-intercepts, and the fact that it's periodic. But we do need to refer to calculus a little bit here and see if we can verify that. So what would be one thing you could do? Say again? I can't hear you. Okay. Okay, you mean just to find a few more points? You work too hard. Okay. I want to do something a little easier. Oh, well, and more calculus nature. What would that be? Let's go back to this. It's your turn. Take a derivative. Okay. L prime of x. The Jesus answer in the first, in Cal 1. Okay. All right. Now, what was that? Ooh, do I really want to do this? What would we have to use? Quotient rule. How does that go? 1 plus sine x. There's our low. Times derivative of cosine x, which is minus sine x. Then what? Minus high, which is cosine x, times d low, which is just cosine x. Okay. And that's divided by low. 1 plus sine x squared. Okay. I will tell you where this first derivative is not defined, everywhere that the function wasn't defined, because you still have that same issue there at sine x. When sine x is -1, it's not defined. Well, that's not going to be a critical value because the function is not defined there. So we'll leave that out. Now the question is, what does that numerator become? Let's see if we can work on that some. That would be a minus sine x, right? Minus sine squared x minus cosine squared x. Okay? Over 1 plus sine x squared. Okay? Now, what I want to do here is factor out a -1 here and make that a plus. Is that legal in most states? Okay? Just factored out a -1 and change both of those signs to pluses. Why would I do that? Pythagorean theorem, that says that's 1. So here, what we have here is a minus sine x minus 1 over a 1 plus sine x squared. But here I'm going to do it again. I'm going to factor out a -1 and change the sign of those, but reverse the order and make it 1 plus sine x. My screen is collapsing on me. That's an x over 1 plus sine x squared. Well, guess what? This one will wipe that one out, and what we have is a -1 over 1 plus sine x. Okay. Now my question to you now is, when is that ever equal to 0? Did everybody see what I did there? It was magic. It was a shell game. Okay. Okay. See how we got there? Okay. When is that ever equal to 0? Say again? Never. Because to be 0, the numerator would have to be 0. And -1 is never 0, ever, not in this universe. Okay. So you have no critical values. And sure enough, my weird looking little things here, this basically ensured that it didn't turn around and go up here. I had in the heart of hearts that it wasn't going to do that. Now we know it didn't. Otherwise, your first derivative would have been a 0 there. It's not. It's never. In fact, it's always. Ooh, no, I can't say that now. Yeah, I guess we could say it, couldn't we? That the denominator, because sine x is always between plus or -1, right? And we know it can't equal -1, so anything else is greater than -1, and 1 plus something greater than -1 is going to be positive, right? So this is always positive, that's always negative, so the slope is always downhill. Hey, look at here, my graph looks like that too. The slope is always negative, because Once the sign goes to -1, that's thrown out again because of first class. Okay, so that's looking even better. All right. Think we need to do a second derivative? Please say no. Well, I guess we ought to. Okay. But this was, did we do? Yeah. This is our first derivative. Second derivative won't be so awfully bad, will it? This is f prime of x. So, okay, so what would be our f double prime of x?
You just take the denominator up, bring up the denominator.
Ah, yeah. Let's rewrite this as, is this what you're saying? 1 plus, or negative 1 plus sine x to the -1? Is that what you meant? Yeah. So let's use that to get our second derivative. And what would that be?
You just change the negative positive and make it positive on that side.
I'm not sure I heard all. Is that to the -2? Is that what you're saying?
Yeah, we'll bring the negative one out and make it positive.
Right. Okay. We got one more little piece to it, though. It's supposed to look like a chain. Hint. Ah, times cosine x. I thought that's what you said. Okay. Cosine x. Okay. Now, written slightly differently, this will be cosine x over 1 plus sine x squared. Is that right? Is that what we got? I think so. Use this one to first take the second derivative. Add a minus sign out in front of it. Minus on minus is plus. This is -2, so that put it down the stairs. But then you had times the derivative of the inside, which is cosine. Now, when is this thing ever 0? When cosine 0. And when was cosine 0? At your half pies, except you can't be at these because it's not allowed there. So sure enough, right there. And here you have a concave up here, concave down here. There, sure enough, is a point of inflection at every one of these half pies, not vertical asymptotic half pies, right? So sure enough, this is shaping up like it looks like it makes sense. Concave up, concave down, concave up, yeah, all the way. Of course, nothing is defined at the vertical asymptotes. All right. Any questions on that? Now, I think this is enough to draw our graphs. If we weren't convinced that was how it looked before, I think we can rest pretty assured that we have points of inflection there. Does this make sense? And they did some test intervals and that kind of stuff, so I'll leave this for you to see. Now their graph may have looked a little better than mine, but we'll ignore that. All right, homework exercises here. I would do all of 5 through, are there any questions before? Let me see, any questions? I know some of this went a little fast, maybe. But if you have questions, please ask. Okay, I would do all of 5 through 8, okay? Only 5 and 7 are in the back and at calcchat.com, but you should be able to match those up pretty well. Okay, then do any of the odds 9 through 35. There's a whole passel of those. They're all at CalcChat, 33's at CalcView. Do any of the odds 37 to 43. They're all at CalcChat, 37's at CalcView. Do any of the odds 45 to 49, they're all at CalcChat. Do 51, it's at CalcChat. 53 and 55, they're both at CalcChat. 53 is at CalcView. 57 is a graphical reasoning. See if you can figure that one out, and that's at CalcChat. There's exploring concepts. 59 through 63, you can explore doing those if you are interested. Then there's horizontal and vertical asymptotes, 65 and 67. They're both at Calc Chat. And by the way, 59 to 63 should be at Calc Chat as well. 69 should be at Calc Chat. Any of the odds, 71 to 75 should be at Calc Chat. And you can investigate doing 77 if you would like. Then there's either 79 or 81. They should both be at Calc Chat. True false 83 or 85 should be at Calc Chat. 87 is a graphical reasoning, as is 89. You can try either of those if you'd like. They should be at Calc Chat as well. 91 is another slant asymptote. It should be at Calc Chat. And 93 is an investigation if you feel investigative. Okay, whatever. All right. This is one long chapter. The next section here is optimization problems, which are fantastic problems. But I really don't think we have time to do those. Are any of you planning to go into thinking like industrial engineering? Is that one of your career goals, possibilities? They use optimization theory a lot in trying to maximize industrial process, minimize things. They do optimization. Well worth a read, but we need to move on, I think. Okay? So let's skip that. I won't test you on that part. But I do want to expose you to Newton's method. Okay? This is one of the handy-dandiest little things. Well, let's see. Let me not do this. I can't do that. Okay. Get out of here. All right. Okay. Good having you in class. Okay. All right. All right. Skipping 3.7, going to 3.8. Believe it or not, I'm going to make a wild guess that most of you probably used Newton's method and never realized it. Okay? Any of you ever use a graphing calculator to find zeros of a function? You were using Newton's method because nothing, I don't think they've ever discovered, has come close to doing it as fast as Newton's method does. So that's basically, I believe, what your calculators do. So we're still applications of differentiation, and 3.8 is Newton's method. Hey, he developed calculus way, way, way back then, and he came up with a method for finding zeros, and to this day, no one's found anything any quicker, I don't think, than Newton's method. We'll approximate a zero of a function using Newton's method. Now, notice the approximation there. That's if you don't have a rational zero. Remember, I had a test for rational zeros, and Descartes' rule of sign gave you real numbers of real zeros, but not how to find real zeros. So if you don't have a rational zero, I don't know of another method to do it. And if you do have a rational zero, yeah, we can do it that way. This will find those that are not rational. And we'll find those that are rational too. The technique for approximating the real zeros of functions, Newton's method, it uses the tangent lines to approximate the graph of the function near the x-intercepts. Okay? To see how it works, consider a function f that is continuous. Needs to be continuous, okay, on some interval a to b, including a and b. Differentiable on the open interval a to b. Okay? Now, if f of a and f of b differ in sign, there's a key. If you're going on the x-axis from a to b, f of a and f of b must be opposite signs. Okay? If they differ in sign, then by the intermediate value theorem, f has to have at least one zero in the interval. Why? It's a continuous function. Okay, if it's continuous, it can't jump over the x-axis, so it's got to have at least one zero in that interval a to b. Okay? So here are the situations here. To estimate that zero, you choose x equal x1, whatever you want to choose that to be. something in between A and B. Okay? Now, Newton's method is based on the assumption that the graph of f and the tangent line at this point both cross the x-axis at about the same point. Now, we'll see examples where this won't work and where all bets are off. But remember, we needed f of A to be one side, f of B to be the opposite side. So here's A, here's B, f of A's up here, f of B's down here. We know there's got to be at least 1 0 in between. Okay? Now, the assumption is that the graph and the tangent line both cross the x-axis fairly close to each other. Now, I'll give you one situation where this will not work. Okay? If your A was over here somewhere, okay, and still positive, B's negative, but A's here, the tangent line's up here, your intercept is down there. Not going to work. Also, where tangent line was 0, it'll never cross here. So those are where it won't work. So basically what you have to have, the function must be heading toward, that's one way of putting it, heading toward its 0. If it is, then pick the next one where it's heading toward that 0. Okay? So the tangent line is going here to x2, the function's going to C, which is what we're looking for. Okay. Now, because you can easily calculate the x-intercept for the tangent line, sure we can, okay, but y equals 0. You can use it as a second and usually better estimate of the 0 at f, okay? The tangent line then passes through the point x1, f of x1, that was where it started, with a slope of f prime, okay? In point slope form, the equation of the tangent line would then be y minus f of x1, y minus y1 is equal to the slope f prime times x minus x1. Okay. Now, these are all calculated. I mean, you know what alpha, you know these values. I know it looks weird having letters in there. They're just actually values. Okay, so you can rearrange this and add the f of x1 to both sides. Y is equal to this. Okay? So now you've got your u value, and you know everything in there except the x. Well, all right. Letting y equal 0, that's where it crosses. Y is equal to 0. You come up with a new x, and that's going to be your x2. So x will be, boy, they skipped a lot here, didn't they? Okay, let's go back here. Okay. What we want is where y is equal to 0. Let me get my pen color back. Okay. All right. Where y is equal to 0, that'll be your new x. So what we have then is, let's do it this way. It's equal to f prime times x minus x1 plus f of x1. Okay. I want to just call that y1, but we'll not do that. Okay. So the new x will be, let's subtract f of x1 from both sides. Why didn't we leave it over there in the first place? Okay. And you have f prime times x minus x1 is equal to minus f of x1. Okay. And then we will divide both sides by f prime. Okay. And then add an x1 here. Okay. Now let's go back. Yep, that's what we had. x1 minus f of x1 divided by f prime of x1. So from the initial estimate of x1, you can obtain a new estimate, which is x2. Okay? Then what you do, you evaluate f of x2 you evaluate f of x1, then you take your x2 minus f prime of x2, and then you calculate again, and soon, so here's what's happening. That first one, you shot here, and you got this right. Your first guess was this one over here. Second guess was this one, right there. Okay? Then you go down here, evaluate f of x2, and f prime of x2, that gives you x3. Okay? Then you come up here, and this is going to aim back down here, and in no time, you're just crisscrossing right there at C. Can I help you? Sorry.
Well, not to stop, I was going to back out. I think I went down to class, actually. It's about some summer courses.
Okay.
Organic chemistry 2 and physics 2.
Okay.
Are they usually offered in the summer?
Yeah, physics 2. I don't know about organic.
Okay.
Yeah, we do offer all physics in the summer.
Okay.
You have to check with Dr. Wilson,
Okay.
Tracy Wilson, about
I said
organic.
physics is what you check with her about organic.
Yeah, the physics 2 is out there already.
We need to put many field in physics 2, organic, all the hard stuff,
Okay.
calculus.
And we'll put her in organic. Too.
Thank you. All right.
Okay. So, I don't know if you can visualize what's happening. You notice x2 is closer to C than x1 was. You do here, and x3 is closer than x2 was. Come up here, do a tangent line down here. Boy, that's going to be really close. And that would be this value, and they just keep getting closer and closer and closer. Very, very rapidly. And I'm almost certain that's the algorithm that your graphing calculators do when they're finding the zeros. Okay? I can't swear to it, but I bet you that's it. Because I don't know of anything quicker than this. Okay? Now, you can prove on x2, calculate yet a third one, which would be x2 minus alpha of x2 divided by alpha prime of x2. And guess what? X4 will be x3 minus alpha of x3 over alpha prime of x3. And you just keep doing it till your error, your difference in the x2 and x3, if it gets really, really close, you figure you're really, really close to being right on top of it. Repeated application is Newton's methods. And these are really easy things to do. Alpha of x2, alpha prime of x2. You've already calculated, you know what alpha is, you know what the first derivative is, you just plug in value after value after value, and it's not that bad. Okay? So, are we out of time? I hear the natives are getting restless. Okay. Yeah, we got it. Okay, what, a minute or two? 4 minutes, okay. Newton's method for approximating zeros of a function. Okay, let's assume that we got a zero at x equals c, but we don't know what c is. Where f is differentiable on some open interval containing c, to approximate c, use these steps. Make an initial estimate of x1. If we don't know what c is, but if you know it's somewhere in there, pick one. Like if you got a graph and you know it's near 3, use 3 as your estimate or whatever. Okay, determine a new approximation. Okay, now, number one, you know f and it's differentiable, so you've already calculated the derivative. So pick that first value, x1, something close to c. Then do 1 minus f of 1, x1, minus f of x1 divided by f prime of x1. Just calculate it. You've got them down there. That gives you the new one. Then keep doing this, until your difference here is within your desired accuracy. If your two consecutive things are like 0.3 apart and you want it to be 0.1, keep doing it. Once it gets less than 0.1, say, hey, that's close enough. I'm happy with that. Or 0.0001. However you want the accuracy to be, you'll get there, and you'll get there rather quickly. Okay. When you do get this, then let your most recent estimate be your final approximation. Otherwise, go back and do it again and again and again. This is called an iterative process, so each application will get closer and closer. Unless they don't, okay? And if you ever see them blowing up, stop, pick another x1. Okay. So let's do that. I don't think we'll have time for this, will we? We'll begin this with example 1 next time. And this, I think, will go pretty quickly. Okay. And 3.8, we're almost through with 3.8. 3.9 is the last section. We do need to do that because you're going to be using differentials forever. So we will do 3.9. So Monday, I'll try to have your tests for Chapter 3 ready for you. Meaning, preaching to the choir here, all of you who haven't turned in Test 1, I need your Test 1, and get your Test 2 in too, so you don't have so many outstanding tests. Okay? So please get them in. Good deal. Any questions? We'll see you. Have a good weekend. Of course, working on calculus will make it a good weekend, right? All right. See you Monday.